Tov, Boker Tov. I suppose that most of the LSEC students are at this conference in Van Leer. That's why so that's a good reason to speak in English and to let them watch the video. It's actually a big problem that we have conferences in the middle of the year. But so just a short recap and some corrections or things I said last time. Not corrections, just want to make sure that things are clearer than. So again, we are talking about parameter estimation, which is this problem of estimating the parameters of a distribution, a family of distributions whose parameters come from some parametric form or parametric space, which is usually a subset of Rn, and we want to generate functions from which we can generate estimators, which are functions of the samples that will be good estimators of the parameters. So as I said, this is it looks like a technical problem. It's actually a very fundamental problem, not only in statistics but also in the theory of perception, and essentially all we do in our brain is some sort of parameter estimation of observations with respect to something which we consider important. And I just want to, so we defined a very important class of estimators, which we call the maximum likelihood estimators, which were essentially those parameters that maximize over all the possible parameters in my class. And as I said, this is in general a vector, some finite dimensional parameter space of the likelihood of the data. And I know that I have to emphasize it, when we think about this likelihood of the data as a function of the parameter, of course it's not a distribution. It's a distribution when I think about it as a function of the sample. But when as a function of the parameter, just a function, that's why you call it a likelihood function. So unlike the posterior, which is a distribution over the parameter, that we at this point ignore. And of course we show that this is equivalent to the argmax of the log likelihood. Let's call it theta prime just to make sure that it's not the correct theta yet, only after. So there is some sampling here with a correct theta if we assume that what we call proper estimation, so the sample actually comes from a distribution in this family. So this is just the log likelihood, doesn't change anything here, of course. And then we actually show that this is the arg mean of all theta prime in my family of the KL divergence, or the cross entropy, between something I call I have to make it clear now, the empirical distribution of my sample to the parameter class. So this is something I showed a little bit quickly through the proof of consistency. And I just want to emphasize again what I said very quickly. I just want to make sure it's clear. So why is this true? So essentially, I define the empirical distribution of my sample. So this is this very intuitive thing. I mean, you have a sample, and you can draw a histogram, for example, of the sample. I mean, just put the samples where they are. So if I want to define it in some more formal way, I usually write it like this, as an integral of sum over deltas. So essentially, think about this as so this is a sum over my sample. Let's call it empirical for any dimension of the variable. So this is, if you want, this is the empirical distribution over x. of my sample. So you have to be, the sample is given, and this is the empirical distribution of the sample. So what I mean by this is, essentially I put the point mass on every sample and just sum them and average. So if this looks a bit strange to you, if x is discrete, let's say through like 1 to 6, something like this, then it's just a histogram of how many times you see 1, how many times you see 2, and so in the sample. Essentially, so this is in the case of at least IID sample. This is what I mean by the empirical distribution. So I write it as a delta function to think about continuous cases, but of course then it means something only when I put it inside an integral, or you can think about it only in first discretize the space into small intervals, and then do the histogram over this interval. So when you do in MATLAB, for example, a histogram of an empirical distribution, you just sort it into the bins of certain size, and this is what we call the empirical. And of course, in the limit of very small intervals, we actually get what we want, and then this will actually get into a delta function. So this is what we call the empirical distribution. It may look a little bit strange right now, but think about it really as okay, you have a Gaussian, and then you actually bin your distribution into bins. Of course, how many bins depends very much on the sample size. I mean, if you want very thin bins, then you need enough samples to fill them. If you don't have enough samples, then take a very, very rough bins. So I can take, for example, bins like this and divide the Gaussian distribution into, I don't know, 6 bins. They don't necessarily have to be of the same size, by the way. Actually, a lot of what we do in empirical data analysis has to do with careful binning of the data. This is really very, very important when you, because in the real world, you always have finite samples. You always need to estimate distributions from this finite sample by some binning, even in continuous variables. And you need to decide what is a good binning, and we'll come back to this question later on when we talk about information again. But so binning or clustering of data into bins is actually a very important issue here. But at that point, think about it just as formally as this type of funny definition. I put point mass for every sample that I see. And the delta function essentially just, that's exactly what it means, a point mass on every sample. Okay? So so essentially it's some sort of an histogram. Okay. Now, then we saw actually that in the limit, so this is always true, and I actually wanted to interpret it as some sort of a projection. So I take actually the empirical sample and project it on my parameter space and look at the point which is closest in that sense of the KL divergence. So find the point theta in your parameter space which is closest to your sample in this KL sense. And you should remember how I did it. And so essentially you should, those of you who like geometry should have in mind this manifold of parameters, each one of them, so it's usually a continuous manifold of some sort. It's actually curved. I mean, it's usually not flat. It has curvature. We'll come back to this issue later on. Those of you who know something about differential geometry, it actually has a local metric, which is not necessarily Euclidean. And so we have a sample. So this is a space of distribution. Essentially, so for each one of these points is actually a distribution. Okay? This distribution, P of x given theta. And I can then therefore calculate for any empirical distribution the distance, the KL distance, in that sense. So I put this here and this here to any point here, Px given theta prime. And the maximum likelihood is precisely the one which minimizes the distance, this particular distance. Not distance, it's this projection. It's not distance because it's not symmetric and has all this. So it's not, strictly speaking, I don't like to call it distance, so I call it usually KL divergence. And this projection is really what maximum likelihood does. Okay? So think about it again in terms of geometry. What you usually call projection is the closest distance, that's the projection to a plane from a point to the plane. It's just putting the point where the shortest distance is. This is a projection to a curved manifold. And of course, in general, as you can imagine, this projection is not necessarily unique or necessarily, there can be all sorts of pathologies here. You need some special properties of this manifold and distribution that you see, such that this projection is really, there's only one projection, and it's completely well defined. We said a little bit about it. Okay, but then I said that in the limit of large sample, this empirical distribution, and this is something which we know how to prove, in the limit of very large sample, the empirical distribution approaches the true one. Or the histogram, if you want, is getting closer and closer. The binning is getting smaller, smaller, and smaller. And eventually I get, so this empirical distribution, and this is, I proved it more or less, but you have to convince yourself again. So this empirical distribution, when n goes to infinity, goes to my true distribution for some theta, from some true theta, if such exists. If my sample actually came from a family, a distribution in my family, okay? So then this will go to the arg mean of the KL over theta prime again, of the KL between the true distribution actually I can divide it by n in this case and ignore the number n here, of my true distribution to any other distribution in my family. And as I said, this also proves consistency, because if my family is what we call identifiable, which means that if the two distributions are the same, if they have the same KL, they have a 0 KL, then they have the same parameters. Okay, so this theta, the arg mean, will be 0 actually, because it's in the family. So the distance will be 0 because it's actually one of the points on this manifold, and it will be the correct one. So this is what that's how we prove consistency. So this led us to the notion of consistency. Consistency of the estimator, which means essentially what it proves. If it's identifiable, then the theta hat is going to be equal to approach theta in probability when n goes to infinity. And the improbability here is swallowed in the fact that I asked it for the DKL itself. Okay? Any questions about it? Yes.
Just in the line for the last line.
This one? Yeah.
It should be theta prime, right? Or in the last line.
Theta prime. Yeah.
And no k, no n over the x in the.
Yeah. Yeah. So I just want to make sure that the empirical distribution is actually a distribution of a sample.
Yeah.
So it's the empirical of the sample. So this is you take the sample, it actually depends on n, and you make an histogram of the sample. That's what I mean. So strictly speaking, the empirical distribution depends on n, but not on the sample. That's why that's what I meant. Okay, you're right. Of course, here we really assumed some sort of independence of the samples, but it's not really essential. I mean, I can talk about empirical distributions also of dependent samples, but ignore it for a second. I mean, the whole thing is still true even for no unknown IID, but then some of the properties we're talking about are not necessarily correct. So implicitly, we also define consistency. This is the consistency in probability. Consistency. This is an important property. So we would like even biased estimators, and any good estimators eventually should be consistent in the limit, because otherwise we don't really know what we're doing. Now, it's actually not such a simple property in complex models. I mean, I talk about really complicated models like HMMs or MDPs or POMDPs or things like this, which you don't know yet. It's not so easy to prove consistency, but anyway, it's maximal likelihood estimate. Now, then we said something else, which was the mean square error, or what we call the MSE of an estimator, which was defined as the expectation, the conditional expectation, condition on the sample. So the assumption here is that I sample again from a certain parameter in my family, and I wanted to see how is this mean square error, or mean squared minus my true parameter square. So again, the picture that you should have in mind is that theta xn, let's do it here. So theta xn, theta hat xn is a random variable, of course. It's a random variable because it's a function of a random sample, so you can have bad samples, good samples, and samples. So this has a distribution, which means that if I look over my theta, just for simplicity, I draw it as a one-dimensional. It doesn't have to be. And so this is theta prime, the all possible parameters. So there's some true parameter, let's say here. This is theta true, the true one. And of course, the probability of this conditioned on my sample, the probability of this over the sample for any given sample has conditioned on this xn given theta. So what I mean by this, I now take the same theta and sample many times. I sample many times, I get different values of the estimator. Okay? So I get different values of the estimator. The point is that, so we'll show today that this actually approach in the limit a normal distribution for IID samples. And it may be that the peak of this distribution is the expectation, the conditional expectation of theta prime. So the peak may not be exactly the same place as the true one. Okay? And of course, so it has two properties which are important for us. One is how much this expectation. So this is distribution over the. So this may be different from the true one, and this is what we call the bias. So if the mean of this distribution of the estimator is not exactly on the right parameter, we call it the bias. Of course, as I said, I mean in general, it's not really clear why it is normal, but we'll prove it later on today. Asymptotically, it's normal. Yes.
But how do you know that your sample is actually representative?
No, you don't. That's why there is a distribution. What do you mean by representative? So I sample many points, many samples.
For every time I only sample, let's say, the picture, okay,
Yeah.
and every time I only sample the right corner.
Okay, so then you have a different distribution. I mean, so the distribution is only a distribution of the right corner of the picture. This is tilted from some other reason. But let's say that there is a true theta, and I always sample from this true theta. Now, if you want to sample the right side of the picture, that's fine. But
let's say you don't know because.
No, but I know that there exists one theta. So actually, here, let's say I'm talking about. Oh, this is an important question. So, theta here is one, belongs to my parameter class. Okay, so let's say I'm talking about Gaussians, and theta is only the mean of the Gaussian. Let's say that the variance is 6. It's 1. Okay, so theta represents here all the possible Gaussians, infinitely many of them, with any kind of mean. Okay. Now, so let's say this is the right one. Okay. This is the true theta. So now taking many samples from this, the samples will be distributed according to this Gaussian. Some of them can be tilted. Some of them can be tilted to the other side. Some of them, as I say, especially small samples, tend to be non-representative in the sense that you can have a small probability, a very biased, a very tilted, or a very non-representative, or later on we call it non-typical sample. But we actually know this is exactly what the theory of probability tells us, and in the law of large numbers in its various forms, that eventually when n is very large, the sample becomes very representative with high probabilities. Probability 1 is going to be typical for n large n, but we are going to say this much more precisely later on. But you're right. I mean, small samples can be off, but the probability of getting a sample which is all here from this distribution is very small. Okay, so I'm going to get samples which are distributed according to this. I'm going to take a finite sample of some size n that I take only 10 points. So 10 points will, on average, can be scattered all over the place, but this is precisely what I mean by the distribution of the estimator. Let's say I take the sample average of 10 points. This will have a scatter, okay? And the scatter is precisely this scatter, the variance here. That's the second number I want to emphasize.
But this is a scatter of many samples, and what I'm talking about is
The scatter of the estimator.
of the estimate, right?
Yeah.
But followed by many samples, right?
It's the scatter over all possible samples of that size.
So, but I'm talking about maybe something a little bit different. That is there a measure for just one sample that it's a good sample? Let's say, for example, what is the difference between the two extreme points? So
If we had something like this, and if you could say on a sample a priori this is a good sample, we would statistics would have been much simpler and much less interesting. I mean, the point is that a single sample can be biased and you don't know it. You know that in the limit of large n, a single sample is going to be representative. But so what is the n for which the sample would be good enough? This is precisely the heart of the theory of sampling. When I want to estimate elections, for example, to estimate the result of an election, I should have a sample large enough to get some guarantee that it's representative. And that's precisely the point of when you take a sample of 1,000 people in the population of Israel, it will be large enough to estimate
there is no feature of the sample itself that can make sure it's good, but only the number.
There's no way that I know, and I think there exists, to take a sample and tell me this is a good sample if it's not large enough. All I can tell you that improbability, which means 99%, this is a good sample in the sense that the probability that this, let's say, the sample mean will not be the true mean is getting to 0 when sample size is getting to be large. This is precisely what we're talking about. This is the heart of the matter. I mean, so how do you know that a good sample the sample is a good sample? It's really a big question. I mean, we don't know. In general, we don't know if we take IID samples, unless n is large enough. But all these games that we are playing about consistency is precisely to make sure that if n is large enough, we're going to be okay. But
What is large enough?
That's precisely where we're coming to. So I want to. Okay, so it's all very good questions, and I'm sure that you're not the only one who asking it, but it should be in the background here. I mean, it should be clear that we are talking about random samples. Random samples will be distributed. I mean, which means that the estimator that we think is good in the limit. This is not good enough for us. We actually, as you actually correctly said, Karen, that it should be. We should have some stronger guarantee. How far is it from the true one for a finite n? So we don't only want to say that it's consistent in the limit. This is a relatively weak statement. We want to be able to say what is the probability that the sample will deviate by more than epsilon. What should be n that guarantee that the probability that it deviates more than epsilon will be smaller than or larger, smaller than delta, something like this. This is usually the type of thing that we are asking.
That's why steps like you take n sample, like n1 point, and then you see what happens to the estimator.
Okay, so this is precisely the mechanism we use already for the sequential decision. In sequential decision, we actually did it online sequentially. We wanted to make sure that we have a good sample. And that's why you put the thresholds to be large enough. That's why I think it's a very important algorithm, or a very important thing to know. So that we actually can guarantee the probability of error, which is really essentially what you want. In this case, you want to guarantee that the value of the estimator is not too far from the true one. But n has to be large enough for that. And we saw that there was this interesting trade-off between the error and the sample size. So the error essentially, the log error over the sample size, behave like the DKL in the limit, and that's why we could actually say something exactly of the form that you want. But this is the heart of statistics. I mean, how do you know that a sample is good enough? This is why people don't believe statistics, because they really don't understand it. How can you say that the election in Israel is going to be decided by a random sample of 1,000 people? I mean, so I don't count. I'm very important. What do you mean you don't count me? But that's precisely the point of statistics. I can guarantee that if the distribution is well behaved and I sampled carefully, which means the correct way that the polls really happen. I mean, so I need to sample exactly the population that is going to vote and in the right proportion and so on and so forth. And this is why it's an art. And then I get a representative sample. But how to do it? It's not easy. That's precisely the heart of what we're talking about. Okay. Now. So again, so this is going to have in the limit some sort of a distribution. Distribution has a mean and a variance, at least. It may not be Gaussian, so it may have other moments which are important. But I'm actually going to show you that it actually has a standard deviation, which is the square root of the variance, which is this width of the variance. Okay. So what we showed is that if we define the bias of the distribution to be the bias of the estimator, to be simply this difference. I mean, how much the mean of the overall possible samples of my estimator for a given n, given sample size, for a given n, this was simply the expectation of this conditional over theta, which means I'm actually sampling for it for some theta, of the theta hat given xn minus theta. So this is the bias. It can be positive or negative. And the other thing was the variance, which was, let me have it in red. The variance was the variance of the estimator. Again, it's a random variable. It should have a variance. Not all randomized will have variance, but this is pathological cases we don't care about here. So, and the variance was what? The expectation, again, with respect to the same conditional distribution given the true theta of what? Of the estimator minus its expectation square. Okay, so and the expectation here is again on the same distribution. Okay, so this is the variance of the estimate, which essentially is the width of this distribution. Of course, what we showed, consistency means that in the limit of large n, this distribution is going to peak, to be very, very narrow and around the true distribution. This is consistency. We didn't say yet anything about how is it going to peak. I mean, how fast we're going to approach this limit. But that's what consistency really tells us. Is in probability, this distribution will be very, very narrow, so the variance is going to go to 0, and the expectation is going to be the true in the limit. This is the meaning of consistency. But now we want to be a little more careful about what do we mean for small sums, precisely your question. And what we showed is that this is simply the variance of the estimator, again, with respect to this conditional distribution, plus the bias square of this estimator with respect to, again, theta, conditional theta. Okay, so this is clear. So, and we said that in general, the mean square error, which is something we want to minimize, has these two terms. And we said a lot. It's probably not clear enough, but it will be clear, hopefully, after you do the exercise about the regression of polynomials to data, what the bias and the variance actually mean. But usually, statisticians assume, I mean, traditionally, that bias is the bad thing, and assumed that they really looked for unbiased estimators. And as we know today, and this is really at the core of machine learning, it's not necessarily true. We want to minimize the mean square error, and sometimes reducing the bias too much is actually going to cost us more than we gain by making it unbiased in the variance, and a large variance is also not good. So in general, we have some sort of trade-off between these two things, and this, remember this, we come back later. All right, so now we want to say something about, we want to assume at this point unbiased estimator. So unbiased estimator means that for every n, the mean of this distribution is going to be at the right place. At the true parameter, at the right place, in the sense that this is the mean of over the samples. Of course, in general, some people ask me here, but you don't have many samples and don't know the parameter. But if I could average over many, many samples, so again, you should ask if I have many, many samples, why should I simply not take a large sample? I just want to make sure that even if I have a small sample, the mean is going to be at the right place. But remember, again, if I'm going to, by shifting the mean to the right place, I'm going to pay with very large variance, it means that my actual estimator can be very bad, because it can be scattered too far. The fact that the mean is okay is good, but it's not what you want because you don't have the mean. You have one estimation based on one sample. Okay, so so you have to be careful in this trade-off how exactly you make it. So now we want to talk about unbiased estimator. So theta hat is unbiased if the expectation again of theta hat over for any n, this conditional expectation of theta hat is just theta for any n, and we want to ask, okay, so if it's an unbiased estimator first, what can we say about the variance? So what is the minimal variance? No. How can it be zero? I mean, if you take 10 samples from a Gaussian, let's say, normal distribution, intuitively you see that something, it can be zero. I mean, the variance is going to have some scatter.
Maybe the limit is right.
In the limit, okay, the limit we already showed that it's zero. This is consistency. But for any finite n, this is not going to be zero. It's going to be scattered around. Okay, the average of 10 numbers is not necessarily has a scatter. That's precisely what I mean. So it can't have a zero mean, zero variance. So what we want, this took me way too much, but it's important. So what we want is something which we call minimum variance estimators. We want, if they're unbiased, then the best we can do is to minimize the variance. Okay, so minimum variance estimators is something reasonable in the case of unbiasedness. Okay, so the question is, what is the minimum? Can we actually bound the variance of an estimator? So many of you, I don't know if this group seems to be missing a lot of the ELSEC people, but how many of you know about the Cramer-Rao bound? Again, not too many. Okay, in this group. Okay, so it's so we do have to show it. So there is a bound. There is a theorem that we want to prove that it's known as the Cramer-Rao bound. It's 1944, again, when in the good times of statistics during the war, people suddenly discovered the power of statistics, and the Cramer-Rao bound is telling us essentially that for theta xn, an unbiased estimator, unbiased, the variance of the estimator from a sample of size n is going to be bounded below by some positive number that we call denoted by Jn of theta, and Jn of theta is called the Fisher information, and it's defined as the expectation with respect to the sample, again this conditional sample, of the derivative of the log likelihood with respect to theta square. So actually, in most cases, so this is definition. Sometimes we call this thing the derivative of the log likelihood, the expectation of the derivative of the log likelihood. We call it the score, Fisher's score. So this is the expectation of the Fisher score square. So if I define S of xn of theta as this derivative, the logarithmic derivative of the likelihood with respect to theta, so this is essentially the variance. So this is called the Fisher score. name. What's really important here is that it's just the derivative of the log likelihood. So essentially, it's telling me if this is 0, for example, it means that the log likelihood is completely independent of the parameter at this point. It's going to be locally insensitive. If it's very large, it means that any small change in the parameter is going to give me a big change. Going to be a big change in the likelihood. So if the likelihood is sensitive to the value of the parameter, the Fisher score, later on we call it the Fisher information. So this is really called the Fisher information. So the Fisher information is essentially a measure of the sensitivity of the log likelihood to the parameter at the parameter theta. Okay, we'll see an example in a second. Now, what is nice about it is that we can easily show that this has all sorts of nice properties. This score, in particular, this is equal, and I want you to show it. This is equal to minus the expectation of the second derivative. Okay. So this is in the one-dimensional case. We can very naturally extend it to n dimension, to d dimension, not to n dimension, to d dimension. But then this will become a matrix, not a number. And this matrix will be called the Fisher information matrix. Actually, the covariance of something. We'll get back to this later. I don't want to confuse you this one. So this is essentially for one-dimensional parameter family. This is just a scalar inequality. The variance of the estimator is greater than the 1 over the Fisher information. Yeah.
Which theta do you take there?
So this is the true theta. I mean, at the true theta. No, but this is bounded by this. The variance of the estimator is, again, I'm talking about this distribution. It's the variance of the estimator, and since the distribution of the estimator is unbiased, centered around the true parameter, so the variance is really the variance with respect to the two parameters. And the variance is at the Fisher information at that value of the parameter. Okay? So this inequality, it's an important inequality. It's called, as I said, has a name, Camara bound. And it's something I want to prove now. So first of all, I want you to notice I'm going to change a little bit the order of things. I mean, those of you, I hope that Noga actually put up on the webpage the lecture notes of Amir as well. So you have the book, which has a lot of inaccuracies, unfortunately, but it's basically okay. And you have the notes, the lecture notes of Amir, which are a refined version of the book in English. It has some differences, and actually my lectures are more or less so far following Amir, and with some additions that some changes that are already added beyond Amir, and some omissions maybe as well. So that's why I don't distribute notes. Essentially, you have notes. But notice that the expectation. So one claim that I want to make, or proposition if you want, the expectation of the Fisher score is 0. Okay. Of this d log p. At this point, let me. Yeah. Okay. I'll keep the n for a while, and then at some point it will be obvious. Actually, I'll talk about one sample. So the expectation of this is 0. Why is this true? So yeah, there's no way you can see it immediately, but actually it's simple. Proof. So we just know that 1 equals the integral of the likelihood over all possible samples. Okay. This is simply a normalized distribution. So I simply take the derivative of this with respect to theta, and what I get is the derivative of 1 with respect to theta is how much? 0. Okay. So 0 equals the derivative of this with respect to theta, but if I take the derivative inside the integral, which all of you agree that I can do, it's actually not so simple. But I assume, of course, that the boundaries are independent of theta. Okay, so so this is simply the derivative of p with respect to theta. But here there is a nice trick. The derivative of p is 1 over p, the derivative of log p, ln p. Okay, so this is simply equal to the expectation of pxn given theta, the derivative of ln. When I write log, I usually mean ln. Okay, so all right, log respect to theta. So why dx? Why is this true? So this is 1 over p. It's cancelled by p. It's 1 over p dp to d theta. So the 1 over p from the log is cancelled. So I put it up again. But this is simply the expectation. Okay. And just to make it's simply the expectation of the log. Okay. Right. Everything it becomes. Okay. So this is simply the expectation. So this proves this little lemma. Okay. So so now I want to prove Cramer-Rao, and I have 4 minutes for this in one dimension. So it's essentially repeating the same idea again. So the proof of Cramer-Rao is simply I have to use the fact that it's unbiased. And actually, we have an exercise for you to show what happens if it's biased. Just repeating the same proof without this assumption. But so if it's unbiased, then I know that the expectation. So this is the proof of Cramer-Rao. So I know that the theta is just the expectation of my estimate. Okay, this is the fact that it's unbiased. So this is the integral over all samples, condition on theta of px. Let's go right this way. Theta hat of xn, p of xn given theta dxn. Okay, I'm trying to write big because I noticed that otherwise we don't see anything in the video. This is big enough. Okay, this is true. This is what I mean by expectation. Okay, but so now I take again the derivative. So I do the same trick again, d to d theta of this equality. So what I get is 1 equal, d to d theta of theta is 1. 1 equals the derivative of this integral, and I play exactly the same trick again. So I take the derivative in and replace the derivative of p by 1 over p, by p times the logarithmic derivative. So this is exactly the same thing that I did here. Is again the integral over all the conditional samples. Theta hat is independent of theta, so I don't have to worry about it. And this is simply p xn given theta times the logarithmic derivative. Okay? So this is precisely the same trick. If you got it there, it's true here also.
The integral is just xn. Why do you write xn?
No, yeah, okay, it's xn. You're right, absolutely right. The condition is here, but I mean that I take if I write expectation, I write it like this. Okay, to make sure that I know what this distribution I'm averaging. This is all possible samples. Yeah? All right. So, but now, so this is simply the expectation of a product of two. So this is indeed the expectation. Let me write it again like this, just notation. The expectation of this theta hat times d log the special score. Okay, it's the same thing. Yeah, make sure that. So it's a product of two functions. It's the expectation of a product. Okay. So what do you know about expectation of product? If they're independent, it's equal. Okay, but they're not independent. So in general, I mean, this depends on the sample, this depends on the sample. The sample creates dependencies. So they cannot be independent. But in general, what we know is something called the Cauchy-Schwarz inequality, which I assume you all know, at least for vectors. So we know that the expectation of xy is actually less than what? The expectation square is less than the product of the variances. Actually, I can say much more than that. What I need here is a slightly different. So I know that even if I shift the expectation of x minus, let me write it like this, y minus y average for any distribution, pxy, any joint distribution, is less than, if the expectation square is less than the variance of x times the variance of y. So this is something which is called essentially Cauchy-Schwarz. It's some generalized Cauchy-Schwarz inequality. Now, if I can prove it to you, but not now. I can do it in the break. We are in the break already. Okay. So if you don't know how to prove it, come to me. It's essentially the fact that the cosinus of an angle is less than 1. Of course, the relation between these two, the correlation divided by the variances, the square root of the variances, is precisely what we call the correlation coefficient. And without the square, it's just a number between -1 and 1. And this is actually a very important thing to know. So correlation coefficient is how dependent. If it's 1 or -1, if the two numbers are correlated, the two variables are correlated. So when do we get equality here? In this inequality? When is there an equality in the Cauchy-Schwarz inequality? Think about vectors in Rn. Okay. So it's as I said. I mean, essentially, this is just the fact that the cosine of the angle is between 1 and -1, and so when two vectors have a zero angle between them, and so the cosine is going to be 1 or -1 if they're either parallel or anti-parallel. This you should know. So which means that equality here is if and only if x is proportional to y. Can be shifted also, because I already subtract the means. So we get equality here if and only if this is true. So this is you all know, okay? The Cauchy-Schwarz inequality. Now I'm out of time. Let's stop here. Take a break and continue 2 more lines from here, using the Cauchy-Schwarz inequality for this. Okay. Oops, I'm out of battery. כמו, רציתי לחבר אותם. וחילקתי בריבה, ואז חילקתי את ההגדר שלו.
זה בדיוק מה שאמרת, אבל
בעצם מציג לך שוויון של אינטגרל.
נכון, הכללה שלי. נראה לי, הייתי להם שדיסקרטי, בסכום, לא משנה, כן.
כן, אז סכום הוא אינטגרל.
הריבוע
משתנה מקרי כללי, אין בהכרח בכלל...
אני יכול להוכיח את זה גם עבור חדות.
כן, כאילו
זה הכל נובע מאותו מקום, זה בדיוק אותו דבר. זה הכל נובע מזה שאוכלת.
פשוט כאילו קשה קצת אולי, כאילו יש שוויון כמו ששווארץ לאינטגרלים בסכומים לבד, ופה אין לך בכפוף הסתברות.
זה בדיוק מה מספיק לי שאנשים יבינו את זה עם וקטורים ב-R2 בשביל להסביר את מה שאני רוצה. מספיק לומר שזה באמת הקוסמוס של הזווית, המכפלה הסטלרית היא המכפלה של האורך כפול קוסמוס של הזווית, היא קטנה שלה לאחד, כל הכללות של זה נבוא להכללה של אותו דבר. גם דווקא בהכללות של זה, נבוא זה לכל את זה. אני חושב שזה לא מה. ברגע שיש מכפלה סטלרית, ברגע שיש מכפלה פנימית, יש לי
אפילו יותר מינורית, מכפלה פנימית.
אז לא שמחה ודיבר. זה לא... זה הכל... האינטואיציה אני מאוד פשוטה. אם אתה מבין את זה בשיטה R2, אז אתה מבין את זה. הוקטורים, קוסם להרביץ ביניהם, קוסם סטטה זה ההפעלה הסטלרית, לא, חולק לנורמה של X, כפול הנורמה L2 בריבוע של Y. אני לא הבנתי את הריבוע, אני לא הבנתי כאילו על מה תנאים לא משנה,
כאילו, אתה פשוט אתה אומר שהנורמה, אתה מחליף את X ואת X להיות הדבר הזה, Y זה והנורמה זה דבר.
שורש של הווריאנס.
כאילו אתה אומר, אני יכול להגדיר ככה
אני תמיד יכול להגדיר את הממוצעים.
ואני יכול להגדיר ככה נורמה.
אני יכול להגדיר נורמה.
זה וריאנס.
אם זה...
זה לא מקרי שאותו קושי המציא את ההתפלגות הזאת שיש לה...
שאלה, למה לא מסתכלים על מומנטים יותר גבוהים? למה מעניין אותנו עד המומנט השני?
בסופו של דבר משפט הגבול המרכזי, שאומר שאם אתה שולט על הווריאנס הזה, אתה שולט על ההתפלגות השיטות של מקבילים. אני לא עושים את ה-very basic thing. אם אתה רוצה לעשות מומנטים יותר גבוהים, יש לנו הרבה מה להגיד על זה.
לא,
אבל זה מעבר למה שאני עושה במקרה. יש בהחלט התפלגויות נורמליות.
כאילו איזה PDF, כלומר,
קומולנטים עומדים הרבה יותר.
זה מהצורה.
אבל למה? אבל לא, שנייה. אבל אף אחד לא אמרת שזה, אתה לא אומר שזה. אתה אמור כאילו... אתה חייב מסבילה אותך.
לא, כי אם זה לא נכון, זה משהו שהוא פשוט מאוד גורם, זה פשוט פקטור.
לא, אבל
זה איזשהו פקטור מול.
לא, אבל...
אז לא יודע,
לא, אני חושב
אולי בגלל שזה PDF, אז זה חייב להיות.
זהו, זה מה שאני אומר, אולי כאילו...
אני באמת לא הבנתי להם.
אוקיי,
סביב זה לאמרת להציג. הצבתי... כאילו סתם, להגיע למצב הזה של קטע בריבוע, כאילו להגיע למצב של סעיף A, שיש לך A, B ו-C, כאילו להגיע למצב כזה, של E וזאת A ו-C, וברגע שאתה מגיע לזה, אז לפי הסעיף הקודם, זה להיות
וזה גם, זה סתם משהו.
זה כולם אותו דבר. גם מין, גם מין. מה זה אומר? למדנו בכיתה, מה זה אומר? למדנו שה-L2 הוא השופלת, L1 זה המידיון ו... אני לא הייתי לכתוב את זה כי בגלל ש... כאילו איך אני יודע... כן, כי ראינו שזה...
רגע, אבל איך... אתה יכול
כי,
לחזור רגע?
כן, זה מאוד מעניין, אני אגיד
כאילו,
איך מחשבים את זה.
את זה שכאילו,
כי ראינו שזה מהצורה הזאת, ראינו שהוא מהצורה של זה, ואז פה ראינו שכל מה שמהצורה של זה, זה בעצם וקסיה.
אבל איך הולכת את זה? יש
את
כאילו
מה?
סתם מעברים לזה?
איך הכנסתי את זה?
כן.
אז פה, אני רציתי לא, כי זה כאלה, זה פשוט דבר עם אי, פשוט פותח כזה. אני לא יודע, זה לא. משהו כיוון רואה? זה ממש ככה, ממש ככה. ועוד זה משתלב חופשי, בדיוק. הנה, אנחנו לוקחים הרי, אנחנו יודעים ש-f של תטא והנה הוא פרופורציונלי ל-f של תטא ול-f של x לפי חוק בית.
זה בייס.
אז זה פרופורציונלי, כי רציתי להתעלם מה...
זה בייס.
בסדר? עכשיו, חצבתי, מה זה f של תטא? חצבתי, f של תטא זה הנורמלי, ומה זה f של תטא? זה בסדר?
אוקיי, נורמלי זה?
כן, בסדר, הצבתי את ההגדרה, פתחתי סוגריים, קיבלתי את הרעיון, אמרתי לו, סתם כדי לא לעבוד באי
סבבה.
וזהו, ואני הגעתי למצב של משהו, זה בדיוק, הגעתי לפעמים, כן, אחרי הסעיף הקודם, זה גדול.
אבל אף אחד לא אמרת למה זה יהיה?
לא, זה תהיה. אני ראיתי ש-f של תטא ו-x הוא דומה למשהו מהצורה הזאת. זה כן.
זה סתם, נכון?
זהו, היה טוב, אבל משהו
אני אומר לך מופע, זהו, עשית, אני שמרתי,
באינטרנט.
כן, כתבת
מה אמרתי שכאילו, מה הדבר שעושה לזה הכי מינימום? זה פשוט תמיד, ראינו את זה בשבוע שלך.
ראינו את זה? כי אני פשוט אמרתי כאילו, ראיתי יש איזה פריים, זה משפיע,
אני חושב שזה בתרגיל קוראים לזה יותר, אבל אומרים נראה לי אבל נראה לי איך אתה גודל, מה זה שווה? אם x בעצם בסופו של דבר הדבר הזה שווה ל... הרי אני תוחם על... כן, מה נגזר הוא שווה? אם x גדול מתטא וכאילו יוצא עם מספר ה-x כן, כן, למה נגזר שזה? זה יהיה x, נכון?
או מינוס
למה?
כי אם xi גדול, אז זה יהיה... אם xi גדול מתטא, זה יהיה...
זה הסיבה, ואז אתה פשוט אומר שזה מספר ה-x'יים שהם גדולים מתטא פחות מספר כי אם, תחשוב, נגיד לעבור איזשהו xi שהוא גדול מתטא, אז איזשהו משהו פה זה בלי הערך זה בלי הערך כאילו, תחשוב על זה כאילו בלי הערך מה היה נגזר שזה בלי הערך? זה פשוט כמה x'יים יש, נכון? כי אני גוזר כל אחד מהם בנפרד, אז זה כמה x'יים אם ה-xi קטן מתטא, אז זה מינוס x'י. בסדר? ואז בעצם זה יוצא לכמה x'י גדולים מזה, ואז זה יוצא, זה שווה לזה, זאת אומרת, זה בדיוק החציות.
ואז זה פותח את מקסימום?
כן, אז הוא אמר לי דווקא, הוא אמר, תיקח תטא, נכון, תיקח תטא יותר גדול. תיקח תטא יותר גדול אז הדבר הזה, אז יהיה לי פחות xi כאילו זה יש לי זה נגזר, וכך זה יותר קטן זה לא מה שאני עכשיו אם אני מזיז את תטא ימינה, אז יש לי פחות xi ואם אני מזיז את עצמו, זה לא קצת לא שאני לא
זה פשוט כאילו, מה שלא הבנתי,
ה-MLE הוא כאילו אינווריאנטי כאילו, אם יש לך איזשהו תטא ML ואתה רוצה לעשות איזושהי פונקציה עליה, אז הוא מסתיר את התטא שקיבלת ואז כאילו, לא שאני נלמד את זה, לא יודע,
All right, so since Karen asked me to make sure that this is clear, I want to make sure that you understand this trick. It's a little it's obvious, but so just notice that the derivative of the log, or if you want the derivative of the ln of p, is p prime over p. Okay? This is all I'm using here. So p prime is, the derivative with respect to theta divided by p. So this has 1 over p, and then this p cancels, and we have exactly the same. So this is simply the logarithmic derivative. There's nothing more here. Yeah. Yeah, so the סוגריים משולשים, these brackets, as we usually we use, this is a standard notation in some circles, like physicists, but it's just a shorthand for expectation. Okay. So when I do this, I'm actually averaging with respect to this particular distribution, the sample condition on theta. It's exactly the same as E, but it's somewhat easier, and I think it's actually a much clearer notation. So don't think about it as physics. This is just notation. Okay. Now, and I'm using it when it's convenient, like here. Anyway, so we almost finished. So we got here that essentially 1 equals the expectation of this product, the estimator, and notice this expectation of our samples at a given theta. So this is what I mean by this conditioning here, times the Fisher score, or this log derivative, derivative of the log of the likelihood at the given theta. And now I average. So what I know about the average of a product is that it's less or equal, simply using the Cauchy-Schwarz inequality in this particular form, slightly generalized, but people ask me where is it coming from. So all you need to really know is what happens in 2 dimensions with 2 vectors. The dot product is always divided by the product of the norms, is a cosine of the angle, and it's in absolute value less than 1. So if I take the square of it, I get it's also less than 1, and it's that's all it is in geometry. I can generalize it to any space which has an inner product in it, in some very general sense, or any Hilbert space or anything that you like. It's still true. So if you're not really sure why is it true for vectors like this, you can read it somewhere. It's quite standard. Okay, so essentially this is just less or equal the variance of the estimator, precisely what I want to bound, times the variance of this, of the Fisher score. But we just proved that it has a 0 mean, so the variance is just the second moment. Okay. So the variance of this is simply the expectation of this log pxn theta to d theta square. So I use the fact that it has that the variance and second moment are in this case the same, because the mean is 0. Okay?
The variance of the log of the probability?
It's the variance of this, of the derivative of the log of the probability, of this Fisher score. And I'm using the fact that the variance is the second moment. Okay? not. By the way, if it's not biased, if it's unbiased, then I have to. It's not unbiased. I'm sorry. If it's biased, you have to. This is not true. But then you have to add the bias and or subtract the bias. Add the bias, and then it becomes true. Of course, what we'll get into it is that you have to take the derivative of the bias as well. So the only difference is that you have to worry about another term which can be big. By the way, if the bias is fixed, if the derivative is 0, then it's exactly like unbiased estimate. I don't get any. It doesn't hurt me. By the way, biasness, as Noga showed you, I think, is not invariant with respect to transformations of the parameters. So if I, for example, somebody asks here, if just because the mean is not invariant with respect to transformation. So for example, the mean of theta is not the same as 1 over the mean of 1 over theta. So any nonlinear function is not, expectation is not, unfortunately, or fortunately, I mean, it makes life more interesting. So for example, the log of the expectation is very much not the same as the expectation of the log, and things like this. So the property of biasness is actually flaky if you have any sensitivity to what we call invarianceness. I mean, so if I'm really talking about in terms of geometry, and I think about those manifolds, the parameters, some sort of coordinates over my manifold, then this property of biasness seems to be not invariant, or not covariant, that sometimes is. I mean, so if I change the coordinates, I will change properties like biasness. To me, I think to you too, it should be a warning that something is probably, biasness is probably not such a fundamental property. You want something which will eventually hold with respect to change of coordinates. And indeed that's the case. I mean, when you take slightly more elevated or more sophisticated view of statistics, then bias is really not important. I care about sufficiency and things like this, but not about variance. If you didn't get this, forget it. Now, now we essentially have, notice, so we can actually sorry, this must be a square root here. So it's the square root of the product of the variances. So so what we get is that if you want this square, instead of putting a square root here, I can put the square there. Well, what I get essentially is that the variance of the estimator is greater than 1 over this number. Okay? This is what this inequality tells me. And this number is precisely what I call the Fisher information for n. So it's independent of the sample because I average over the sample, but it's a function of theta. Okay. So essentially this is the proof. Now, a few things that we want to know. So how is this? So there's a lower bound that any estimator obeys. Any estimator in the world has a variance. What is this J of n? So in the IID case, Jn of theta, this expectation of the log square, it's actually easier to see it if you use this property that I didn't prove, but I want you to prove. It is actually equal to the minus the expectation of the second derivative. I'll use this notation now because I see that most of you are not familiar enough with it. So again, at least for a one-dimensional case, this is simple. This is, again, I take the same expectation. So I simply said that the expectation of the second derivative is the same as the expectation of the first derivative squared. This is something I want you to show. It's a good exercise. But if this is true, again, now in the IID case, what do I know about the distribution of the sum? So the log is the sum. I mean, the probability is the product, and the log of a product is the sum. And what I get here is the sum. Of the expectation with respect to one sample only, but it's all the same. and of course, since it's all the same, this is simply second derivative, sorry. It's true also for the second derivative. I take a derivative of the sum and then the second derivative of the sum. It's all right. So this is n times what we call J1, or sometimes simply call it J theta. So J theta is just J1 of theta for one point. Okay? So in the IID, and this is important that it's IID because otherwise it's not necessarily true. In the IID case, so far I didn't assume it. I know that this Jn of theta is simply n times J of theta. So in this IID case, I know that so the variance of the estimator, in this case, is greater than 1 over n J of theta, where J of theta is the expectation of one sample, just a simple distribution. Either this or the square of the log, the first derivative. Now, by the way, the second derivative, okay, we'll see immediately why it's important, it's the second derivative. So in most cases, you'll see this as the Fisher inequality, because we assume IIDs. And what you see here is that indeed, when the sample, the J of theta is independent of n, this is for you. So when n goes to infinity, the variance is at least bounded only by 0. So, but it's as long as n is not infinity, for any finite n, there's a lower bound on the variance. Okay. So now, two questions that you want to ask. Okay, what type of estimator will achieve inequality here? This is the minimum variance estimator. Okay, so this is the minimum possible variance. I cannot go below this. It's a property of my parametric distribution. And maybe it's a good place to show an example. So let's show an example. So far, everything looks very abstract again, but it's really simple once you actually work with the real distribution. So let's take an example before I continue. It's one of my problems. I always tend to ignore the examples, but they're very, very important. So an example. I can take the normal. Let's take a simpler one, an exponential parameter. So P of theta is 1 over theta e to the minus theta x. X and theta are positive. Okay. So this is what the exponential distribution. It's almost the simplest. I'm wrong. It's either in the I want it to be unbiased. So I want the mean to be an unbiased estimator. So which one I should take? X over theta? Okay. So 1. Yeah, that makes more sense. So I think you already showed, I hope you already showed, that the maximum likelihood estimate for this distribution is what? For theta? Yeah, so theta maximum likelihood in this case is simply the sample mean. This is easy. Okay, so we know this already, but when we know it's unbiased. It's also unbiased. So what do we know about the Fisher information in this case? So how do you calculate the Fisher information? Very simple. Take the log and take the derivative and average. Okay, so the Fisher information, I write Px theta is minus, allow me to do it in one step. So this is taking the log will be minus ln theta minus 1 over theta ln x. So it's the derivative of minus ln theta log ln, it's the same here. Minus 1 over theta x, okay? Now I take the derivative, so what's the derivative of ln? Minus 1 over theta plus 1 over theta square x. Okay? And so taking the average now, I want the Fisher information. I want J1 if you want, or J of theta, just the average of this square. Actually, it's easier in this case to take the second derivative. And you see that they're equivalent. So I can take it square, or I can take the second derivative. In this case, you can convince yourself on this example that it's really the same. So maybe just take minus the second derivative and then average. So this will make plus 1 over theta square and minus 1 over theta 2 times 1 over theta third, and x. That's the only thing that depends on x is x in this case. So the average of x is what? Theta. Okay, so it's 2 theta. And then I don't need to average. So I did it too quickly, maybe. So what I did here, I took the second derivative, so it's the expectation of the second derivative of log px theta respect to theta. Okay? So the second derivative again is minus 1 over theta, so it's going to be minus 1 over theta square. Plus the derivative of 1 over theta square is 2 times the derivative of 1 over theta 3 with a minus sign. Theta to the third. And then I take the average with respect to x. So it's the only thing, it makes this theta. So it's minus 1 over theta square plus 2 theta, 2 over theta square, which is just 1 over theta square. Okay? So this is the Fisher information in this case. Very simple. You'll play with it a little more. So it's actually very simple. You know? Just take the functional form, take 2 derivatives, or if you want, square it and then average. It's the same thing, and you get a function of theta. Okay. So yeah.
So in this case, the variance of the estimator is
no. By the way, it's good to show that the maximum likelihood estimator, in this case, actually it's unbiased, and that it's actually also what we call minimum variance. But this we have to show. Okay, so yeah, actually for calculating the Fisher information, of course, I don't need to know anything about the estimator. It's independent. For any estimator, the Kammer-Rao bound holds. But the question is, which estimators actually achieve inequality? So we want to actually give it a name. So estimators which are minimum variance again in engineering, by the way, you see this all the time everywhere. Minimum variance estimators, it's one of the things I really like to do, and especially electrical engineering. So you see it in the title of every second conference paper in engineering. Minimum variance estimator or something. So the minimum variance estimator, minimum variance unbiased estimator. Yeah, something like this. So the question is what? So we say you actually call it. So definition, if you want, theta hat of xn unbiased is called efficient בעברית אומרים יעיל, למרות שנשמע לא יפה. efficient if what? If the variance of theta equals 1 over nj, which means it's a minimum variance. Okay. Now, the theorem that I want to, it's called sometimes asymptotically efficient if it's becoming efficient in the limit of large n. Okay, so the theorem that I'll try to prove, it's actually a bit nasty. One of the ugliest things that I mean, it's not clean what we do there, but we do it anyway. So the theorem that we want to prove is that the maximum likelihood estimator, if it's unbiased, it's actually we know that it's asymptotically unbiased. What do you mean by asymptotically unbiased? Consistent. Yeah. So it's asymptotically unbiased and efficient. Okay. So theta maximum likelihood always for IID samples is asymptotically which means n goes to infinity, is consistent. We know already is efficient. Okay. Asymptotically efficient, it means that the variance for large n is going to be exactly 1 over n, or you're going to approach the limit 1 over n, the efficient information. So maximum likelihood estimators, at least asymptotically, behave very well. I mean, they converge to the true parameter, and they achieve the minimum variance. So why is this true? So essentially, and the intuition of the proof is very simple. If we can argue somehow that the estimator of a maximum likelihood estimator, if this is ML here, is indeed normal due to some sort of central limit argument. I mean, if I can show you that the estimator can look like a sum of many independent variables, scaled correctly, so I have to divide it by 1 over square root of n, or multiply by square root of n in this case, then if under the right scaling, as you know, the central limit theorem, I hope all of you learned it, and it's really important to scale things correctly. So if it's going to be normal, then first of all, I know it's going to be unbiased, which means that the theta is going to, the expectation in the limit is going to center in the right place. And then what's going to be the variance of this estimator? So how many of you heard about the Hessian matrix in some other forms, maybe? So you know that the second derivative of the log likelihood in the limit is precisely the Hessian matrix. So this is why I insist on the second derivative, because this is precisely going to give me the bound of the. So this is going to look like the log of it is going to look like a parabola. That's what we mean by Gaussian. And the second derivative of the parabola is exactly the width of the inverse of second derivative. Yeah, the minus second derivative. It's precisely. So that's why it's minus second derivative here, because this is going to be a negative number, and the minus of it is a positive number, of course, that was also showed. And this is, so essentially you already see, or at least you should see, that this is going to work for us very nicely. I mean, that this second derivative here is actually going to fit exactly the Hessian of the distribution. So it's going to approach the limit of the variance. But we need to actually show it more precisely. So this is an intuition, but it's a good intuition. So what we do is we take, so the maximum likelihood is precisely the point for which the derivative is 0. The derivative of the likelihood, or the log likelihood, is 0. Okay. So what makes perfect sense is to take this log likelihood. So let's denote it like Amir does, though it's not a very good notation, because the function it still depends on the variable. But simply the log of pxn given theta. So L prime of theta. It's still a function of xn. I'm going to average it in the end. L prime of theta is the Fisher score. Okay. d log p to d theta, and L double prime is precisely the second derivative, okay? And so on. So I can in principle take theta not too far from theta ml, which means I'm somewhere here near the center, and take a, and this is exactly why I'm a little bit cheating, but not too much. So I'm going to take a Taylor expansion of this L prime near this point. So L prime of theta is going to look like what? Around theta ml, so it's going to be L prime of theta ml. This is the first term of a Taylor extension, okay? Plus, but this is what? L prime of theta ml. It's precisely 0, because ml is a maximum likelihood. So at this parabola, at this peak, at my estimator, this is precisely where the derivative vanishes, okay? So, so this is going to be 0. Plus, what is the linear term? So it's theta minus theta ml. Yeah, around the estimator, the maximum likelihood estimator, times what? Times the derivative of L prime, which is the second derivative. Plus other things. Okay? Where did I cheat? No. Okay. This time. Okay, so essentially, so this is just Taylor expansion. It's not equality. It's a second order approximation. Okay? Now, but if this second order approximation is right, and I have to justify it, and this is precisely where I'm going to use the central limit theorem. That's where it's getting a bit tricky. So if this is true, then I can write, okay, this is 0. So you see that theta minus theta ml to this first order approximation is what? Is minus, and this is L double prime. So it's minus L prime of theta ml. No, sorry, minus L prime of theta divided by and again, this is at theta ml. So this is L double prime at theta ml. Why? Because no minus. No minus. Sorry. This is true. Okay, so now that's where I feel a little uneasy, but this is the way the proof goes. Let's look for a second on these two terms. I mean, what is L prime of theta, and what is L double prime of theta? So remember, L prime of theta is actually L prime. It's actually the derivative of log pxn given theta to theta. In the IID case, this is simply a sum. Sum I go over n of this d log pxi to d theta. So this begins to look like what I want, in the sense that it's a sum of independent variables, which are identically distributed, actually. Okay? So if I want to use the central limit theorem, I want to say that something like this is going to distribute normally. And what should I do? So I should probably divide it by. So again, simple intuition: sum of random numbers like this is going to grow on average like third of n. Okay, it's not growing like n because the mean is 0. Remember that the mean is 0. But it's going to look like a sum of random variables drawing with zero mean, and this grows in general like square root of n. This is something, some intuition that all of you should have. It's always true. So if I divide, I divide it by square root of n, this will actually remain of order 1. Okay, so let's do it. So I know that 1 over square root of n, this sum. So these are IID numbers. Okay, again. So the sum is going to approach in the limit, and this is what I mean. This is exactly the central limit theorem. We're going to approach in the limit a normal variable with what? With zero mean. Okay, the mean is still 0. What is the variance? So it's the average over. So it's exactly going to be the Fisher information square. Variance. Fisher information? Yeah, the Fisher information, sorry. It's going to be the variance of this number, but since it's divided by n, it's going to be precisely this. No, the variance of these numbers is the Fisher score. This is the Fisher score, the sum of the square of the Fisher score, remember? This is the variance. It's 1 over when I use already the Cauchy-Schwarz and moved it to the other side, then it's 1 over. But this was the definition of the Fisher score, the variance of these numbers. Okay, so this is the central limit theorem. Okay, I don't have too much time to really get into it. So it makes perfect sense to really okay, and let's see what so L prime of theta divided by square root of n. So 1 over square root of n L prime of theta is going to, in the limit, have this this distribution. And similarly, you can see that L double prime of theta is just going to behave like n times the Fisher information. Why is this? So again, I'm summing here a second derivative. So here it's simply the second derivative. So I know that the average of every one of the second derivative is precisely the minus the Fisher information. So this double prime is going to look like this. Sorry, there's a minus sign here. Okay. So so this looks like n times Fisher information. This is what we showed before. Yeah. We showed that second derivative of the log score goes to n times the Fisher information in the IID case. This 1 over square root of n goes like Fisher information. So if I scale theta minus theta L by square root of n, n divided by square root of n, I get something which is approximately normal distribution. So the consequence of this a bit convoluted argument is the square root of n theta minus theta ml is going to square root of n here is going to approach a normal distribution with 0 mean and the variance, which is j 1 over n, j over n. One over n j. Yeah. And 1 over square root of n. So yeah, 1 over n. Sorry, 1 over j, not 1 over n. 1 over j. Yeah. So this is just an argument. I simply look how is this behaving in the limit of large n, and I look at two asymptotic things. How the numerator behaves for large n, and how the denominator behaves for large n. And I see that they both behaves like 1 over n like 1 over square root of n, a normal distribution. So this, the ratio is going to behave like 1 over square root of n, a normal distribution with 0 mean, and 1 over j 1 over j variance. Okay, so this is essentially the ugly proof that I really don't like because it's not very transparent, but it's true. I simply looked at, so this is first order, the way this difference between theta ml and theta behaves on to first order in theta minus theta ml. And you see that this difference on its own behaves like 1 over square root of n, a normal distribution. Or if you want, square root of n, that's what I wrote here, square root of n theta minus theta ml is a normal distribution. 0 is 0 mean and 1 over j variance. Yes? That's right. Okay, so I know this is something I proved last time, that the theta ml is consistent. So I know that in the limit of large n, it's going to be close to theta. That's what it means. Theta ml approach in probability theta in the large n limit. So I can really assume that this is a small difference. And now I simply expand around it. And that's why I'm a little bit cheating. I mean, if you feel uneasy about it, you're all right. I'm taking only the second term extension. And then I look at how is this second term extension behaves, and I show, using all these arguments, that this is sum of many independent variables, and this is sum of many independent variables whose variance is known. And therefore, this is going to approach n times the Fisher information. This behaves like a random variable. So this is approaching. This is a number. It's approaching n times j. And this is a random variable which has a distribution with square root of n j variance. So if I 1 over square root of n j variance, if I multiply it by square root of n, I get a normal variable. It's written in Amir's note in more or less the same way. And at this point, I don't know how to say it more clearly. So essentially, you can actually, this is something, it's a true argument, but I know that the proof is not very convincing because of this ratio of two limits, but it's true. So in the limit, this is going to behave normally, and we also show that the variance is going to be precisely what we expect it to be, 1 over nj. Or the standard deviation is going to look like 1 over square root of nj. Okay, so this is good. I mean, so if it's true, then everything is nice. Let me show you just one more thing about maximum likelihood estimators, or one more thing about the Cramer-Rao bound. So this, I mean, this argument here, if you want, is more or less the proof of this theorem. I don't want to say it any to elaborate more. This is it's what we call it's really just an outline of the proof. It's, some details are missing, but it's all right. We'll never ask you to prove it in a theorem in an exam. Here, the second derivative is negative. Second derivative is negative because I'm in the maximum. So it's the same minus that appears in the second derivative all along. J is positive, and the second derivative is negative. Okay, so I want to ask, okay, what type of distributions in general will be efficient, not only asymptotically? When can I told you before that, so I can ask, going back to the Cramer-Rao bound, we know what is the condition for equality there. We call this. It's if the two vectors are parallel. Okay, so what type of, the question is, what type of distributions achieve equality? it's again a little tricky because again, as I said, the unbiasedness is something I don't want to hold to carry with me too long because it's not an invariant property. But what kind of distribution have equality in Farmer-Rao? So again, this means that that these two things, equality in Cauchy-Schwarz means that these two variables are linearly dependent. Okay? So this means that d log p x theta to d theta, this is the variable which generates the Fisher information, whose average squared. The variance of this is the Fisher information. This is the Fisher score. Should be proportional to what? To this variable x, which in my case was the estimator. Okay? So this means that there's some constant which may depend on. So this is now as a function of x. So there is some function of theta. Let's call it b of theta times some other function. I'll call it b, little b of theta. I know it's a bit confusing. I should call it a because a is plus b, but never mind. Times the estimator.
B again is the bias?
Hmm?
B is the bias?
No, so it's really not a good choice. Let's call it a. Okay, it's just a constant. Okay, I'm saying that it's proportional, and there might be another constant. Another, let's call it b. Let's call it c. I don't know. A constant which may depend on independent of x. So the function. I'm talking now about linearity. So this is the condition for equality, that the Fisher score is a linear combination of the estimator. So it's proportional. So since I'm subtracting the mean, I can have an offset there. So it doesn't matter. Okay. But now it's very simple. Take and integrate. I can integrate this over theta. So it means that log p. So this is the condition for equality in the Cauchy-Schwarz inequality. Yeah? Clear? Equality in Cauchy-Schwarz is if the two vectors are parallel, which means that these two variables are proportional to each other, a linear function of each other. So this, now I integrate over theta, and I get that log p x theta. So the only thing, sorry, there's no function of theta. Yeah. It's independent of x, a function of theta. So I now have two other functions. Let's call this one b of theta. I want to be consistent with the Amir notations, and this one theta of x plus some big C of theta. So this big C is the integral of little c. Doesn't matter. Now, since I do an integral, there can be. Now I integrate with respect to theta. It's a general integral, so there can be a constant of integration. So there can be another function. Let's call it d of x. Okay. So this is what I see, that the distributions that achieve equality for any n, not only asymptotically. D of x. Because this is the constant of integration. I integrated with respect to theta. Okay? Constant of integration. Okay. So in general, so I have two variables. Now, in general, this is a function, this is n, not only x, but okay, so this is right n here. It just makes things a little more complicated. It's the same thing.